Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to talk on the module Density of States and Potential Applications of the Semiconductor Nanostructures under the paper Nanoscience and Nanotechnology First. So after completing the module, students will be able to first, the electronic structure of the semiconductor nanostructures, that is bottom up approach, will be discussed. Second, the density of states in 1D, 2D and zero dimensional systems will be discussed. Thirdly, the potential applications of the semiconductor nanostructures will be discussed in detail. So students, let us start with a basic introduction about the module. To determine whether a material is a metal or an insulator and to calculate the magnitude of the current under applied bias, we need the density of states, which, as you recall, is a measure of the number of states in a conductor per unit energy. So the concept of the density of states is used in many areas of physics. For example, it is important for reaction rates in nuclear physics, the calculation of specific heat capacities, black body radiation, phonon spectra, and so on. The DOS, that is density of states, arises naturally and early in statistical physics. To calculate the average quantities in statistical physics, one could do an integral over the phase space, but this is typically very complex. So the alternative is to express the variable of interest in terms of the energy of the system. So the volume element in phase space is replaced by a weighing factor in an energy integral, which is often much easier to work with. So this weighing factor is the density of states and it is the subject of this module. So let us first discuss about the bottom-up nanocrystals approach, which is a large molecule, considering it to be a large molecule. So the method to explain the unique properties of a quantum dot is based on the bottom-up approach, while the quantum dot is considered as a large molecule or a cluster. So the simplest instance of a multi-electron molecule is that of a diatomic hydrogen H2. In this molecule, two atomic orbitals combine to form a molecular orbital that spreads out over both the hydrogen atoms, namely a bonding and an antibonding molecular orbital. So the bonding molecular orbital is lower in energy compared to the individual atomic orbital, whereas the antibonding molecular orbital has higher energy than that of the individual atomic orbital. The molecular orbitals are occupied by the electrons in such a way that the potential energy of the molecule is minimized. In the H2 molecule, the two electrons originally in the 1s atomic orbital of the individual hydrogen atom are accommodated in the bonding molecular orbital, thereby leaving the anti-bonding molecular orbital unoccupied. So the highest occupied molecular orbital is referred to as the HOMO, and the lowest unoccupied basically molecular orbital is called as LUMO, LUMO. Similar method can be applied to the large molecules, clusters, and also the bulk material. So as a molecule acquire bigger size, number of atomic orbitals combining to create molecular orbitals rises, resulting in progressive increase in the number of energy levels and gradual decrease in HOMO-LUMO energy gap as shown in this figure. So every molecular orbital MO group possesses a definite energy. However, MOs having intermediate energies are more than those having energy values near the maximum and the minimum values, that is completely bonding or completely anti-bonding. It implies that MO states having maximum density at the intermediate energy values and reducing to minimum density are so numerous and so closely distributed that they form a quasi-continuum, an energy band equivalent to conduction and valence band. So the HOMO level is at the top of the valence band, while the LUMO represents the bottom of conduction band as shown in this figure. So the semiconductor nanocrystal may be considered as a big molecule or a cluster consisting of a few tons to a few thousand atomic valence orbitals, producing equal number of molecular orbitals. Thus, its electronic structure can be described by energy bands having high density of energy levels at intermediate energy values and discrete energy levels close to the band edges, wherein MO states have low density. In addition, HOMO-LUMO energy gap is greater than that for bulk and also size dependent, increases with decrease in nanocrystal size. This describes both the quantum confinement effects referred in earlier section from the molecular viewpoint. Density of states in one-dimensional, two-dimensional, and zero-dimensional systems. In semiconductor nanostructures, the free motion of carriers can be limited to 2, 1, and 0 spatial dimensions. So the density of states defines the number of states available in a system and is important for deciding the carrier concentration as well as the energy distribution of the charge carriers in a semiconductor. So in semiconductor nanostructures, free movement can be restricted to two dimension, which is known as quantum wells. If it is in one dimension, quantum wires, and zero dimension, quantum dots. So GE represents the density of states, and the variation of GE with the energy E is shown in this figure for the bulk 3 dimension, sheet 2 dimension, wire 1 dimension, and a dot 0 dimension. So students, let us now discuss how the density of states are calculated for a 2D semiconductor. So in order to calculate the density of states for the 2D structure, that is a quantum well, similar approach can be employed, but the earlier equations undergo following change. That is, here we will assume a k-space volume of the single state cube inside the k-space, that is V single state is assumed to be pi by a multiplied by pi by b equal to pi square by v equal to pi square by L square. So the k-space volume of sphere within the k-space V circle equal to pi k square, and the number of filled states in a sphere comes out to be capital N equal to V circle divided by V single state multiplied by 2 multiplied by half multiplied by half. So this is equal to k square L square by 2 pi. Now by putting k equal to root of 2me by h cut square, we obtain capital N equal to ml square e by h cut square pi. So now the density per unit energy can be calculated from the chain rule as dN by dE equal to dN by dk multiplied by dk by dE equal to L square m by pi h cut square. So the density of states per unit volume and per unit energy can be obtained by dividing above relation by V. So GE for 2D is equal to L square m by pi h cut square by L square equal to m by pi h cut square. As mentioned before, for the electrons having mass m tending to m star, thus GE for 2D equal to m star by pi h cut square. So one important consequence of the above relation is that the 2D density of state is independent of energy. Immediately upon reaching the top of the energy gap, significant number of states becomes available. Let us now discuss the density of states in one-dimensional system. So in order to calculate the density of states for a 1D structure, a quantum wire, the previous equations with the modification can be employed. That is, the k-space volume of a single state cube inside the k-space. It is given by V single state equal to pi by L, and the k-space volume of the sphere within the k-space, that is V line, equal to k. So the number of occupied space states in the sphere, that is capital N, equal to V line divided by V single state multiplied by 2 multiplied by half equal to KL by pi. Now after replacing k by root of 2me by h cut square, we obtain n equal to root of 2me multiplied by L by h cut pi. This is equal to root of 2me multiplied by L by h cut pi. So the density per unit energy can be expressed as dN by dE equal to dN by dk multiplied by dk by dE equal to 2me to the power minus half ml by h cut pi. So the density of states per unit volume and per unit energy becomes GE1D equal to 2me to the power minus half ml by h cut pi divided by L. So this is equal to m by h cut pi root of 2me. Now further simplification gives us GE for one dimension equal to 1 by h cut pi multiplied by root of m by 2e. So for the electrons, m is replaced by m star. Moreover, as only the kinetic energy is being considered, E is tending to EC. So GE for one dimension equal to 1 by h cut pi multiplied by root of m star divided by 2E minus EC of states for 0D can be expressed by using a delta function, that is GE0D equal to 2 delta E minus EC. So this figure shows the functional dependence of the density of states on the energy of semiconductor. So we have the electron density of states for the semiconductors having 3, 2, 1 and 0 degrees of freedom for electronic movement. Systems with 2, 1 and 0 degrees of freedom are termed as quantum wells, quantum wires and quantum dots respectively. Pi a multiplied by pi by b multiplied by pi by c equal to pi cube by v equal to pi cube by L cube, where V is the volume of the crystal and V single state denotes the smallest unit within the K space which is essential to hold an electron. V sphere by V single state multiplied by 2 multiplied by half multiplied by half multiplied by half. So here the factor of 2 accounts for the 2 probable electron spins in each solution, and half is the correction factor for redundancy in counting the identical states plus minus nx plus minus ny plus minus nz. So the number of filled states in a sphere comes out to be capital N equal to 4 pi k cube L cube by 3 pi square. Potential applications of the semiconductor nanostructures. Quantum dot, which is 0 dimension. A semiconductor crystal that confines electrons, holes, or excitons to 0 dimensions. Quantum dot or QDs, because of their high extinction coefficient, are principally promising candidates for optical applications. They work like a single electron transistor and demonstrates Coulomb blockade effect, increased resistance at small bias voltages. So controlling the size of a quantum dot leads to several promising applications. For example, larger quantum dot exhibit greater redshift compared to the smaller ones and less pronounced quantum properties. Conversely, the smaller particles allows one to take advantage of more subtle quantum effects. Being 0 dimension, quantum dots have a sharper density of states than higher dimensional structures. Accordingly, they exhibit superior transport and optical properties. They have potential uses in diodes, lasers, amplifiers, and biological sensors. Crucial challenge of ensuring proper gate control over the channel can be readily resolved using nanowires owing to their large aspect ratios. So by wrapping gate dielectric around the nanowire channel, good electrostatic control over the channel potential can be achieved. Similar to FET devices, where the variation in conductance is controlled by change in electrostatic potential, gate electrode of conduction channel charge density, a biological or chemical FET works by detecting the variation in charge density which characterizes the recognition between a target molecule and the surface receptor. The variations in the surface potential affect the chemical effects similar to the gate voltage effects, resulting in a detectable and measurable change in the device conduction. Quantum wells 2D. So the effect of quantum confinement becomes apparent when the well thickness approaches the de Broglie wavelength of carriers, electrons, or holes. Due to their quasi two-dimensional nature, electrons in quantum wells have a density of states as a function of energy having distinct steps versus a smooth square root dependence similar to the bulk materials. So, moreover, the effective mass of holes in the valence band becomes comparable to the electrons in the conduction band. Both these factors, along with the reduced amount of active material in quantum wells, results in the enhanced performance of quantum well based optical devices such as lasers, diodes. So, consequently, quantum wells are extensively used in diode lasers, including red lasers for DVDs and laser pointers, infrared lasers in fiber optic transmitters, or in blue lasers. They are also employed to fabricate HEMTs, high electron mobility transistors, which are used in low noise electronics. So, quantum well infrared photodetectors are also based on quantum wells and are used for infrared imaging. So, students, let us now summarize what we have learned in this module. First, the electronic structure, basically semiconductor nanostructures, that is bottom up approach, was discussed. Second, the density of states in 2D, 1D and 0D systems were discussed in detail. Lastly, we discussed about the potential applications of the semiconductor nanostructures. Thank you.